Hi, folks. I seem to have figured out how to make this work now, so I'm hoping that you'll be able to see me. There's a minute left to go. The chat's working. Should hopefully be able to send me some messages. If you've got any questions regarding any of the paper, I will. I've got one viewer. I've got 3 viewers. What I'm going to do is, it is 6:29, so I'm going to hang around for 1 more minute till past, so anyone who's still waiting to log on at past will be there for when the thing is. Can I ask a favor? Can someone send a message on the chat just to check that this is all working? I have the chat off to my right, so when I'm reading the messages and what you'll be able to see on the screen, hopefully it'll all be relatively synced up. See if I can share screen. Oh, there's the chat window. Application window. Let's do share. So you should now be able to hopefully see question number 1 of the paper 2. It'll pop up in 10 seconds. There we go. Brilliant. Okay, so 6:31. Well, shouldn't take us too long. Hey, I've got a message off Josh saying, I can't read that, Josh. I don't understand what you've just said. I think it's A. Are you trying to be the Fonz? A. Okay, right. Question number 1. Let's go through the paper. It shouldn't take too long to do it. So question number 1 was answered universally well by the year group, which I was happy with. There were a couple of students who'd done silly mistakes and just not reading through the question carefully enough. So easy question. Particles present in the nucleus of both atoms. So we know that the only particles that are taking place in the nucleus are the neutrons and the protons. Then, of course, these questions are quite clever because they increase in difficulty kind of continuously as the questions go on regarding these isotopes. So the atomic number of atom L is number 6. Now, the reason for that is that both atoms L and M have got 6 protons in their nucleus, and the protons are what decide what the element is, and also its atomic number, hence atom's number. I have Josh sending me jokes on the chat, guys. So I'm going to continue to ignore him. The mass number of atom L, right, so what we need to do is, in order to get the mass number, it is the protons plus the neutrons. So we look at atom L in the table, and we've got the number of neutrons and the number of protons being 8 and 6 respectively. You add those together and we get 14. So that's our atom's mass number. Then it says, oh, clicked over to the next page. I don't know, I want to keep it as a full page view because it's slightly easier for you guys to see it rather than the spleen split. Right, atom L and M are neutral because atoms on the periodic table are always neutral, and they're neutral because the electrons, which are negative, equal the number of protons. So if I have, in this case, if I have 6 electrons, which would be -6, and 6 protons, that would be +6. Hence, the atoms are neutral. Next, use this information in the table to explain why atoms L and M are isotopes of the same element. So you can see my answer. Now I've gone into probably more detail than I need here. Gin Man wants me to wait. So we've got atoms L and M have the same number of protons. So they are this. Now, the trick to this question was you needed to say for 2 marks, there's 2 questions here. Use the information in the table to explain why atoms L and M are isotopes and of the same element. So we've got 2 independent questions there that we need to answer. So the first thing I've done is to explain why they're both the same element. And of course, the particles that decide what the element is the protons. And L and M have both got 6. I should have taken the number out of the table, to be honest. I would really have liked to have amended this. And I did this under exam conditions. So I would have liked to have said both L and M have 6 protons, so they're the same element. But L, so we've got, so why are they isotopes? L has 8. Now you'll notice I've done something important here, which is I have used the data in the table. I've said L has 8 neutrons, but M has 6. So therefore isotopes. Because we've got to take that data from the table. I think a lot of students didn't get that mark because they weren't saying the numbers from the table. I don't actually think necessarily the question required you to do so, but you should always attempt to. Next, the electronic configuration. Well, if we've got 6 protons, we've got to have 6 electrons. We know the first shell is the smallest and it holds only 2. Therefore, there's only 4 electrons in the outer shell, so that's going to end up being 2, 4. And of course, the element's carbon. Scroll down to the next one. Right. The melting points of 3 related compounds, capric acid, formic acid, palmitic acid, are as follows. Draw the graph. Now, by the way, please note bar chart. Yeah. It is important to make sure that if they tell you to do a particular type of graph, please do so. Now, there are lots of different now you can see the bar chart I've drawn, and I'm going to put my hand up here and say, I didn't use a ruler. Sorry about that. I didn't have one on me at the time. Please, year 11, don't forget your rulers in the exam. They just won't like it. I've made an effort. The only one that really mattered was the palmitic acid, because its number was, I think, 63, which meant it was running through a box. And you could clearly see, I'm running my mouse over at the moment, that it was a very easy. Now, you could have done the bar charts as thin bar charts. You could have made them thinner. I've made them as wide as possible. I figured they were actually wanting that in the question, but it didn't really matter. The next question, by the way, the graph question was fine. The majority of students got both marks. This one was terrible. Students are finding it very difficult in order to figure out what the state is of substances at room temperature if you're given their melting point. They told you also in the question that the boiling point was way over 100. So none of them are going to be gases at room temperature. And if you look at capric acid, it shows that the room temperature is below its melting point. So therefore, it's going to be a solid. These are questions that definitely need practice, and I'll be quite happy to do some practice of these during the revision sessions. Formic acid was the only one of interest. The melting point is below that of room temperature. So it's going to have melted already. At that temperature there, it's past it. So it's going to be a liquid. And of course, the palmitic acid is also going to be a solid. So we continue on to the next one. The apparatus can be used to investigate electrolysis. So this is question 3. Right, really, by the way, can I just say, I loved this question. It was a lovely setup. It has 3 electrolytic cells. These are called electrolytic cells, all joined in series to each other. So we've got 3 sets of electrolysis going on simultaneously. So the questions, though, were relatively straightforward. Name the particle that moves through the wires. Now, we know that wires are made of metals, and metals have 3 delocalized electrons that are able to move. It then said the electrodes are made of platinum. And it says, which is inert. Explain what is meant by inert. You had to just have one word for this, folks. You didn't have to do any sentences. You didn't have to do any extended writing. It was just, the word inert means unreactive. Right, this one was the first one of any difficulty with the electrolysis question. Explain why the electrolytic cell containing lead bromide needs to be heated before the electrolysis can occur. 2 marks. Now, there was quite a lot here to say for those 2 marks. First thing you had to say was that lead bromide is ionic. You had to state the structure. And therefore, it can only conduct when molten, as the ions are free to move around when molten. And then you notice it's 2 marks, so we need 2 distinct points. Now, I think a lot of people lost the mark because they wrote it was ionic, and then the ions weren't free to move. Lots of students were writing down that they have free moving electrons. Please don't. Only 2 substances have free moving electrons, and that's graphite and metals. Ionics don't. All the electrons are localized onto the ions, so they have free moving ions. But what we then needed to say was explain why it couldn't conduct when solid. So when solid, the ions can't move to carry the charge. Lead needs to be heated to melt it so that the ions are free to move. That was a tricky question, that. And it definitely required a little bit of thought going on. Right, this question was a very, very, very difficult question at this point, because the problem was you had 2 cells joined together, but then what it did was it focused on the sodium chloride solution that was in the middle of the 2 others. And it said, name the gases formed at each electrode. Now, the nightmare about this is there were 3. Now, this is going to require a little bit more understanding, because the one that most students didn't know about is that you make oxygen at the positive electrode. Now, if you look at my half equations below, so now just to explain that this is a very unusual question. I've been teaching 10 years and I have never seen them do this. I have never seen them want students to recognize that at the positive electrode, you actually make a mixture of 2 gases. Now, just to tell you that you actually only make about 5% oxygen and 95% chlorine, which means the oxygen often just gets ignored. I've never seen a question where it was asked. So it's something to bear in mind. It's important for you guys to realize that this is the dominating reaction. The chloride ion will lose its electrons and become chlorine. However, the OH minuses as well, a few, very, very few, but some will be pulled into the positive electrode and will, although it's not related to chemistry. Yeah, so helpful. Yeah, I know, and yes, I know. There's people on the live chat who are just being silly. I'd really like it, guys, that if you've this so far is the most tricky question on the paper. If anyone has any real questions, do post. I will reply. So yeah, at the positive electrode, you do make 2, but there's 95% chlorine. You need to make sure that you've got in your head, I've never seen the oxygen appear before. So keep that in mind. It's not a common occurrence. They do want you to know that chlorine is the major gas. At the negative electrode, of course, is hydrogen, not sodium metal. The reason being is, of course, that the hydrogen is less reactive than the sodium. So the hydrogen ions will collect 2 electrons and form hydrogen gas. And of course, then it's nice to consider redox at this point, oil rig. Oxidation is loss, and loss means spitting out. the two gases are both losing electrons because they're products. They're being spat out of the reaction, whereas the hydrogen is gaining them. So there's your rig. Reduction at the negative electrode where it's gaining electrons, and its oxidation loss at the positive electrode where the two gases are formed.
Why is the answer not?
Hydroxide. Zara has asked why the answer isn't hydroxide. Hydroxide's not a gas. Hydroxide is the ion that's produced when water splits apart, hence why the extra product along with hydrogen and chlorine is sodium hydroxide with a tiny bit of oxygen as well. But hydroxides are ions that make solutions alkali. You can't have a hydroxide gas. All hydroxides are bases, or alkalis. Technically, actually, not entirely true. Whoa, whose voice was that? Miss Childs? Why can't oxygen be a half equation? Nah, that's a lovely question. Right, because there's no O2 minus ions. Oxygen exists, of course, as oxygen gas diatomically, but we always use the periodic table to work out that it's O2 minus. There isn't any of them. To get an oxide ion, you would need to melt something like magnesium oxide. And if you melted magnesium oxide, you would make oxygen gas via two O2 minuses going to O2 plus 4 electrons. You would. But you don't in the anything that's in solution. There are no oxides which are soluble in water. And if you did have an O2 minus ion, it would react with water to form hydroxides anyway. But those are all tricky questions. I'd love it. Julia, please, could you do me a favor and make a note of that question? Because it's a really good question, that. And I'd love to show you that question on a whiteboard. It would be a lot easier for me to explain why it's not there. Great question, though. Best one so far. The voice wasn't Miss Charles, by the way. It's Miss Donna. Right. First calculation. This was a disaster. I think, right, guys, you need to get into your heads that but 1 Faraday. Okie dokie. Good one, Julia. Like it. So 1 Faraday is 1 mole of electrons. So if they ever quote a Faraday, you just go moles of electrons. So you can see what I've done here in my working. I've written down the equation again, which I probably think a little bit odd, but I did that because I could show my working. And the ratio between the copper 2 plus and the electrons is 1 to 2. And I'm going to try and make my mouse go big. Because of this bit here, there is 1 copper 2 plus 2 moles of electrons. So what this means is they have told me here, I'll make my mouse big again, the 0.04 Faraday is 0.04 moles of electrons. So you can see that I transferred that down to here. I've then shown that I've divided it by 2 based on the mole ratio. So I've now got 0.02 moles of copper, times that by 63.5, and I get 1.27 grams is what I end up with that. I shouldn't really have done, by the way, I've actually made an error there. I shouldn't have done it, the electrons to copper 2 plus. I should have done the electron mole ratio to copper metal, but it makes no difference in reality because the ratio is the same, 2 electrons to 1 copper atom. So it makes no difference that I've done that, but technically it is a slight error on my behalf. I did, as I said, even as a chemistry teacher of 10 years, you're still going to make slight errors. You can never get away from them. And it's an important thing for you guys to recognize. Errors will always be there. What you've got to try and do is practice to make sure you minimize them. That's the important bit. Right. The next question, it says an excess. Now that's an important bit. An excess of dilute hydrochloric acid was added to a lump of calcium carbonate in a beaker. And it then says the mass of the beaker was recorded every 30 seconds and the graph was shown below. So let's have a look. Right. So you can see the black line. And of course, some of the questions were quite straightforward, but year 11, I seem to be finding this as a universal thing across the year group. Students are not recognizing what the word observation means. Yeah, the word observation means what you see. Excuse my spelling of disappears. I'm an idiot. So we've got, I was rushing through it at this point. So number one, what are you going to see? Fizzing. Why? We're making a gas in the equation. We're going to see CO2. So this is going to fizz. Do not write down, I saw a gas. Can't see CO2, it's invisible. The next thing is the limestone. It's going to decrease in size. I've suddenly realized I've made a mistake. I've just lost my first mark on this paper. I would have got all the rest of them even with the subtle errors, but this one I'm just going to have lost. Oh, hang on a minute. No, hang on. Who was in excess? Excess dilute hydrochloric acid. If there's more acid, the limestone disappears. I'm correct. Sorry, I apologize. I suddenly thought the limestone was the calcium carbonate was in excess. It wasn't. The acid is in excess, which means all of the limestone will be used. It is going to disappear. So fine, that is correct. You're not going to see water. You're not going to see the salt being made. You're not going to see the acid change because the acid is colorless anyway. The only two things you're going to see is fizzing or effervescence, if you want to be posh, and then you're going to see the calcium carbonate decrease in size. That you will see over the time, but it will also disappear entirely by the end of the reaction. Right, give the test for carbon dioxide. This was a disaster. Guys, you can't just write lime water. You can't do it. You must say bubble the gas through lime water. Turns cloudy. I love the year 7 answer. I would prefer it if you would start shifting over to, if you form a solid and it turns cloudy, the correct term for cloudy or solids appearing is a precipitate. So we're going to form a white precipitate of calcium carbonate is what you see. So watch out for that. It's nice, by the way, you're allowed to say cloudy year 11. They do allow it. I don't like it. I think it's a little bit babyish and you guys are way beyond that now. But you are allowed to say it. But bubble through lime water is a clever trick that lots of students just say, you use the lime water test. I'm not entirely sure why I did the voice. But you use the lime water test. And that you need more. You need to say that you bubble the gas through it. By the way, that question commonly comes up as a diagram. They'd ask you to draw the apparatus. I should have done it on the side, to be fair. Okay, next one. So it then says, describe the relationship between the mass of the beaker and its contents and the time. Right, guys, I'm very sorry for this. There has been some confusion in one of my revision lessons. I nearly said my religion lessons. My revision lessons, and students have made a bit of a mess of this. Please note how many marks this question was. Just 1. What that meant is lots of students were saying it went really quickly at the beginning and then slowed down towards the end and then stopped at this time. You didn't need to do it. All you needed for 1 mark, that's only if it was 3. All you needed to do was, as time was increasing, the mass decreases because we're losing carbon dioxide gas. That was a disaster, and I feel partly responsible for that. So that question requires you to be a bit more careful. If it's 1 mark, keep it simple. If you're asking for 3, you're going to have to go into a little bit more detail about how the rate's changing over time. Next, how many minutes did it take to stop? This was a mess, by the way. Oh, year 11, this was poor. Right, when does it level? Everyone is saying 3 minutes. Everybody said 3 minutes. It's not 3 minutes. It's still not level. You need to get your ruler out, put your ruler from here to here. Whoops, send it below. Here to here on the other end, and you'll notice that it stops there, 3.3. And they allowed 3.3 to 3.5, anywhere there. And everyone was giving 3 minutes. Everybody. Very few people. I think about 5 people in the whole year group got 3.3 to 3.5. And that was just, it's something that we need to work on. Graph questions are a nightmare. I know they need practice. I'm expecting to see you guys coming up to see me with your mobile phones, with screenshots of questions that you've been doing that you couldn't do. Come and find me anytime. I can explain anything in 5 minutes flat. And I can do it a lot better than over a webinar. It's nice to get everybody done here. And of course, this is saved so people can watch it back. Next, I put 3.5 minutes, by the way, and I only just got it. State why the reaction eventually stopped. All the calcium carbonate had reacted. Because the acid was in excess, all the calcium carbonate had been used up. So the reaction ends when that runs out. The reason why the acid didn't run out is because it was in excess. Right, this question was universally answered badly. Identify the compounds other than water present in the solution. Put your hands up if you put CO2. Why can't you say limestone instead of calcium carbonate? That's a really good question, actually. The reason being is because calcium carbonate has 3 different forms. You can have chalk, limestone, or marble. In reality, did the question say limestone at any stage? Let's just scroll up. What did it say anywhere? No, it said calcium carbonate. So they want you to be using those words rather than limestone. Go figure. It's just they haven't used the one in the question. Who put that? Jin Man, gain a mark. You can have one. That's definitely correct. So 3.5 is correct. You are allowed it. So you can have it. Extra mark for Jin Man. I'll change it on your sheet. Right. So, okay, this was a mess. I need to explain this quite carefully. The hydrochloric acid, I like it, Jin Man saying, yay, she got an extra mark. So after 2 minutes, what compounds are left? Any others? Like carbon dioxide is not there. It's bubbled away. Yeah, it's gone off into the atmosphere. It's not one that you're going to quote. Just to point out, by the way, that some of it does stay in the solution, but it's a very, very small amount. And it just deemed negligible. So they wanted you to say leftover acid. We know the acid is in excess, which means it will always be there. Even at the end, even after 5 minutes, it's still going to be there. After 2 minutes, the reaction hadn't ended. So the calcium carbonate, there's still going to be some left. The next thing, of course, is you're going to have calcium chloride, which is the salt that we've formed. The CO2 has bubbled away. So that was the main loss on that one. After 5 minutes, the HCl that was in excess is left. Only calcium chloride now remains because all the calcium carbonate has reacted and has gone. So those are the 2. Tricky, that one. Right, the experiment was repeated using the same mass of calcium carbonate, but as a powder instead of a single lump. On the graph, draw the graph. Right, so I went up and I quickly sketched my line, and you can see what I've done in red. It's come down steeper. And the reason why it's come down steeper is the steeper the line is, the faster the reaction. We know that surface area increases rate. So it's going to increase, so it's going to be steeper coming down. We're going to make the mass is going to be lost quicker. And it also ended earlier. That was one of the key things. You had to end before the 3.5 minutes because the powder will go and just be done. And it'll be very, very rapid. Powdered always goes much quicker. Chemists prefer powder, greater surface area. By the way, most students did really well on that graph question, which I was really pleased about. Okay, right. A student uses this apparatus to find the increase in temperature of water when methanol is burnt. Okay, write a chemical equation for the incomplete combustion. The trap here was they told you the product, didn't they? Lots of people threw in carbon. Lots of people threw in carbon dioxide. They didn't read the question. If it's incomplete, it's going to be CO2. It's going to be CO or C. And in this case, they told us carbon monoxide. They could have just said a toxic gas. It's far more common. So the methanol, which they'd given us the formula. The formula was up here. Lots of people missed it. The methanol plus oxygen goes to CO and water. And it already balances with the 2 in front of the water. There's 1 oxygen here, 2 oxygens in the oxygen, and then there's 3 on that side as well. So that all added up. Next. State another reason why the increased temperature is less than expected. Heat loss to the surroundings. We always know the top reason is going to be heat loss. They would have also accepted you have to heat the glass beaker. The thermometer is going to absorb some of the heat. Loads of reasons. Impurities in the fuel, maybe it wasn't pure methanol, but the top answer there, guys, is heat loss to the surroundings. Let's keep going. Right, next one, dropped you into calorimetry. Right, first thing I did to gain my first mark, I had to work out the temperature change. So I found the highest temperature of 58, minus 22, and I got a change of 36 degrees Celsius. Then what did I do? Right, Q equals MC delta T. So 125, which was the mass of the water, times by 4.2, times by 36, gave me joules. That should go straight in, 18,900. Right, now this was ridiculous. It required 4 marks. Guys, I'm so sorry. I hope there was a bit more space there for you. I've got all 5, I've squeezed them in, but flipping heck, that was very, very tight to get 4 marks. So the first thing I needed to do was I needed to convert the joules to kilojoules. So there's my first mark there. 8, by the way, I should have put units in. 18.9 is kilojoules. I've converted the joules from up here. I've divided it by 1,000 to put it into kilojoules. What I then did was that I wrote down my equation over here of delta H, enthalpy equals Q over N, raw energy over moles. I wrote then delta H equals 18.9 divided by, and I didn't have this number. I realized where the 4 marks were coming from. I needed to work out the moles of methanol I had burned. So my next equation appears, which is moles is grams over rams. I needed to know how much fuel I'd burnt, which was 1.5, divided by the MR, which they'd given you in the question, to give me moles. So that's moles of methanol. Put that into the N of this equation. We do Q over N, and I got 403. And then I must remember, I've had to put in that sign. This is exothermic, so it must be negative. That one is the most common mark lost on a GCSE paper. They always forget it. Keep it in mind. Next, this one was a disaster. Everybody wanted to join them with a line and to say activation energy. That wasn't the issue. The issue was, look what we've drawn and explain why what we have drawn is wrong. Not complete the diagram, not what is missing. It's what mistakes have we made already. This question was a disaster, and it's something to bear in mind. By the way, I'm just going to let you know, I have never seen this graph without a line between. So it was really, really mean, that one. They wanted you to say, number 1, it was exothermic. So the products should be lower than the reactants. They then wanted you to realize that the reactants on the shelf here with methanol should have also had oxygen on it. There were 2 mistakes they had already made. Not what was missing, but what were the mistakes that they'd already done. So that one was a tricky question. Even I had to think about that, because I wanted to write down as well. I was like, hang on a minute, can I not say that there's a missing line? But then I realized, I was reading the question going, there's mistakes in the picture. And when I checked the mark scheme, it said, do not allow missing line to across reactants and products, because it wasn't a mistake that had already been put on. I thought it was a really clever question, to be fair. That's a grade A question, that 2 marks that many people won't get, bear in mind. Next, right, onto our good old burp. So bond data, you always run burp, reactants minus products. And they had drawn it out for you. Now, because my page isn't formatted very well, I went on to the next one, but you'll see what I've done. I've written out the equation again. I didn't draw it. I should have drew it. I apologize for that. But then what I did was I added up my bonds. Look what I've done. I counted on the previous page. I've got 1, 2, 3 CH bonds, 1 CO bond, 1 OH bond, and 1.500 bonds. I added them up, found the values in the table, put the multiplies in, and I got a total of 2,803. 1 mark. Next, total Labonza. I got 3,338. 1 mark. Right. Here's burp. Reactants minus products gave me minus 535. There's the 3rd mark, and the final answer is your 4th. It wasn't actually a bad question. Lots of students had done very well on it. I think a lot of them had clearly seen what they needed to do, but they didn't show they're working out very well. Can I also say, by the way, that some of you guys had written in the correct numbers and then the answer was wrong. You'd just done the wrong calculation on your calculator. Don't throw away those marks, year 11. Don't do it. They're the easiest marks to get. Just make sure you've got a rough idea what it's going to be so you don't make an easy error. Like somebody got like 200 from this calculation, and I was like, how did you get that? So just bear it in mind. Next, magnesium and its compounds have many uses. Magnesium is never found as an element in the Earth's crust. Explain why. Magnesium is very reactive, so would have reacted with oxygen in the air. So you find magnesium, not as magnesium, but as magnesium oxide. It's also found in seawater as magnesium chloride. It's reacted with the salt in the water, but that's what they wanted. They wanted you to say it's very reactive. It would have picked up oxygen. Next, magnesium can be extracted from seawater in multiple stages. Which stage involved a neutralization? This was done pretty well by all the year groups. I think everyone spotted the hydroxide being the alkali and the hydrochloric acid being the acid. So acid plus alkali, salt and water, there's your neutralization stage 2. Just look out for the acids. Next, suggest the name of the other product formed from stage 1. Stage 1, they added calcium hydroxide to magnesium chloride. And they told you made magnesium hydroxide. If you've swapped, the magnesium has stolen the hydroxide. The calcium must be left with the chloride. That was poorly answered. Don't know why students didn't get that one. Definitely something to have a chat with people if they're not sure. What happens to the ions in magnesium chloride whilst melting? They become free to move. That's it. If you melt magnesium chloride and you melt it, the ions become free to move. That's it. That's all that happens. Next. We're nearly there. It's been a quick one. Write the half equation for the reaction at the positive electrode. Like the chloride ions, it's the usual thing. We've seen this before. It was actually asked already on the paper, which I apologize for because it means that there are 2 marks there. If you couldn't get one, you couldn't get the other. But the chloride ions are going to lose their electrons and become chlorine gas. Right, the next few were a disaster. These were universally through the year group answered badly. I need to walk you through it very carefully and explain it bit by bit. So, the manufacturers made magnesium by electrolyzing magnesium chloride. To calculate the mass of magnesium chloride needed to make 48 kilograms of magnesium. Right. Now, have you noticed? The first thing to notice here is that they gave you kilograms of magnesium. They gave you kilograms of magnesium, and they want your answer in kilograms. What this means is you don't have to worry about the conversion to grams. You can just keep it in kilograms. So I've now done grams, and we know the equation, folks. Grams, moles is grams over rams. So we've got 48 kilograms divided by 24 gives me 2. Now the correct number would actually be 2,000. Because if I'd converted to grams, which I should have done because the equation says grams over rams, but it wasn't needed, would have been 2,000 moles. Now, therefore, 2 moles of magnesium chloride. MR, because, guys, the ratio is look, and I've written it here. If you take magnesium chloride and you rip it in half using electricity, you make 1 magnesium and 1 chlorine gas. It's a 1-to-1. Which means the moles of magnesium is going to be the same as the moles of magnesium chloride. It's a 1-to-1. So 2 moles or 2,000 moles of magnesium chloride. Then, of course, there was a mark for working out its MR. 24 plus 35.5 times 2 gave you 95. Then, of course, that's your MR. 95 times by the 2 gives you 190 kilograms. So that was a tough question. And again, Talk about lacking space. This has been squashed to within an inch of its life. And I apologize for that, folks. It doesn't half make it tricky. Next, calculate the mole in electrons needed to make the 48. Right, that's the trap. In moles, which means I need real moles. First thing I did is I rewrote the equation. The equation was already given to me at the top up here, but I wrote it down again anyway, so it was in my vision, it was in my view. And it says 1 mole of magnesium 2+ ions needs 2 moles of electrons. What that meant is I could now go grams over rams for magnesium to get me moles of magnesium. And you'll notice I have done the immediate change from kilograms over to grams over here. I've times it by 1,000. So then I've divided that by 24, the relative atomic mass of magnesium off my periodic table, and I got 2,000 moles of magnesium. I doubled it due to the ratio to get 4,000 moles of electrons. Right, we're on to the last one, folks. This has been a short but sweet visit. So, and here's the answer. Right, these, I cannot begin to tell you how many of these I have seen over the last 3 or 4 weeks going through the GCSE papers. They love their salts. Make sure you're well practiced, because this is 5 marks. This will be an entire grade boundary. If you get this wrong, the problem is as well, if you get it mixed up, if you write down the wrong method, you'll score nothing. There is very little similarities between them, and they need distinct processes. I think that's why they like them. These are the grade A star questions, folks, because students can't do them. Right. So I broke it down into steps, and I would expect you, year 11, to do exactly the same. Don't try and put this into a paragraph. Break it into steps and just give me good quality sentences. Mix solution of H2SO4 with magnesium oxide. Now, just to tell you, this is an important one. If you ever mix a solid with a solution, you should probably heat it. The reason being is chemical reactions require activation energy. So heating them is usually a good idea. You'll speed it up, otherwise it might take ages. The next thing is, so once you've heated it, make sure that you have MgO in excess. Now this one, I don't think anyone got this, that you have to have the MgO in excess. Now to explain why, this is because in a minute, you're gonna have to boil off some of the water. And I tell you what, I don't know about you, but I really don't fancy boiling acids. It's not a good plan. So you want to make sure all the acid is used. And the magnesium oxide doesn't matter. It's a white solid. And I'm going to filter it out now. So it just says, keep adding the MgO until it's in excess. Filter out the excess. You want to use up all your acid because acids are nasty. Right, once you've filtered out your MgO, and you had to filter that out first, what you then do is you heat the mixture to reduce the volume. You don't want to remove all the water, because if you remove all of it, you won't get hydrated crystals. You need some water there. So you want to reduce it to about half. This, guys, this is a bit like cooking. If you wanted to cook rice, the one thing you don't want to do, you always add too much water. Because if you boil away all the water, the rice will start to dry out again. You want hydrated rice. So you add lots of water, you reduce the volume down so the water is then absorbed. And then, of course, with salts, you leave them in a warm place so the water can slowly evaporate and the crystals will form. I really wanted to tack on a step 7 of, and then filter out your crystals. But you can pick them out with tweezers if you like. It wasn't required on the mark scheme. But a really interesting paper, a really nice mix of questions. It had some really difficult calculations that show the extent of doing triple rather than dual. Yeah, you're definitely going to need to be better, more versed in doing your calculations. Definitely you need to have your salt preps absolutely ready and raring to go for your real exam papers, and practicing things like graph skills. I am happy to spend as much time with anybody as they need if you've got another paper that you're doing. If you do a paper at home, take photos of it with your phone, bring in the questions you're not sure about. I will do them with you. I will. This is easy. Easy, easy, easy. Right, let's see if I can turn this screen share off and get back. Hey guys, so we're all done for today. I hope it was useful. Let me know tomorrow if you found it useful, and if you've got any other papers that are being done, any questions at all that you've got about what's happened, and you need any further assistance, just give me a shout. Thanks for coming and watching, guys. It took 45 minutes in total. It's not too bad. And I will see you guys in the school tomorrow. Have a lovely rest of your evening. Bye, guys.